Hello, students. This is the fourth video that I have decided to make for you, and perhaps this one might be the most important. And the reason I say that is because what I'm going to try to demonstrate to you here is going to be new to you, whereas in the prior videos, much of what I hit upon could have been considered review, stuff that you perhaps knew how to do and just needed a little refresher on. But this material that I'm going to present to you here is material that is going to get you through our unit on trig identities, and so you're going to find this something that you're unfamiliar with. So I'm hopeful that you are able to learn from this this demonstration. It would certainly be a better situation if we could have some give and take, some conversing back and forth. It'd be better if we were in the classroom for this, but I'm going to do my best to try to be as comprehensive as I can and to anticipate the sticking points, the points where things that you may get confused upon. So I'm hopeful this is helpful to you. The goal here is to develop what I call the identity toolbox. So that's our goal. When we're done, the intent is that you will know the items that are in this toolbox, and you will have an understanding from where they came, how they're derived. So you will use this identity toolbox initially to do something we call simplifying trig expressions. And then a little later, you'll use the items in this toolbox to solve what are called identity proofs. But the items in this toolbox, to be clear, you are responsible to know. I guess you could say you have to memorize them. And don't let that scare you so much. Let me tell you, first of all, that when I'm done here, you'll see that there are 11 tools in this toolbox. Now that may sound like a lot, but here's the good news. You already know 8 of them. So there'll be 11 equations, if you will, 11 statements that just simply say that one expression is equal to another expression. So, and I said to you that you already know the first 8. So let's start with the first 6. So right now, what I'm going to start doing here is filling in this toolbox. And once again, in the end, you're going to be responsible for knowing all of these items. The first 6 items in the toolbox are nothing more than the reciprocal relationships that you familiarized yourself early on. And it's very simply this. We know that the sine being the reciprocal of the cosecant would be equal to 1 over the cosecant, which means that the cosecant is equal to 1 over the sine. The cosine, being the reciprocal of the secant, would be 1 divided by the secant, which means that the secant is equal to 1 divided by the cosine. The tangent is the reciprocal of the cotangent, which means that tangent is 1 divided by cotangent, and cotangent is 1 divided by tangent. So there's the first 6, and those are referred to as your reciprocal identities. The next 2 you're also familiar with. We learned long ago that the tangent is equal to the sine over the cosine, and that the cotangent would then be the reciprocal of that, the cosine over the sine. So there you have the first 8 tools in the identity toolbox. Let me try to explain to you how you'll use these tools before we get the next 3. There's 3 more here. All you will do when you're using these tools is you're going to substitute. There's going to be a point in time, there's going to be types of problems where you're going to want to substitute one thing for another. And of course, you can only do that if the things are equal. And this is just really a listing of things that are equal. So you may want to, at some point in time, substitute the expression sine over cosine for tangent. Or you may, at some point in time, want to substitute 1 over sine for cosecant. You'll have reason to do that in the problems that are forthcoming. Now, we have 3 more items, 3 more tools in the identity toolbox. But I need to explain to you where they come from. And to do that, what we're going to do is we're going to go back to an old friend, the unit circle. So, and this will be something that's not complicated. This will make perfect sense to you. Okay. So here's a circle. We're going to call it a unit circle. You're very familiar with this schematic here. I'm going to put an angle here. I'm going to drop an altitude, and I'm going to call this vertical leg Y, and this horizontal leg of the right triangle X. And then we know that the radius here is 1. We learned that this point right here on the unit circle has coordinates X, Y. But we also learned that those 2 points, X, Y, are really cosine, comma, sine. So as you work your way around a unit circle, every ordered pair that corresponds to every point has coordinates cosine, sine, of whatever this angle is. If this is theta, be cosine theta, sine theta. But I want you to look for a moment just at the right triangle. And early on you learned, probably 7th grade, your 7th grade teacher probably said to you, a squared plus b squared equals c squared. You learned the Pythagorean theorem. If you would apply the Pythagorean theorem in this situation, instead of a squared plus b squared equals c squared, you could say that y squared plus x squared, those are the 2 legs, would equal the hypotenuse squared. But the hypotenuse is 1, so that would equal 1 squared. Now, when you look at this relationship here, and you know that x is cosine and y is sine, you could do a little substitution. If you put sine in for y, you're going to have sine squared. And if you put cosine in for x, you're going to have cosine squared equals 1. This, students, is an identity, a critical, often applied identity. The sine squared of an angle plus the cosine squared of an angle will always, always give you 1. Now, I want to make sure you understand what that means. If you wanted to, you pick an angle, I don't know, 37 degrees, just to pick a number, plus the cosine squared of 37 degrees. I guarantee you, you plug this in your calculator, you're going to get 1. So that becomes the 9th identity in our toolbox. The sine squared plus the cosine squared is always equal to 1. Now, I'm going to write that here, and I'm going to play around with it a little bit to get the 2 remaining tools in our identity toolbox. I'm hopeful that when you see this right here, sine squared plus cosine squared equals 1, you just think Pythagorean theorem. That's all it is. And we're taking the Pythagorean theorem, we're applying it to this right triangle inside the unit circle, and that's what you would get if you plug these expressions in for a squared plus b squared equals c squared. Now, I'm going to take this relationship, and I'm going to go through, and I'm going to divide each term by cosine squared. Now, sine squared over cosine squared would be tangent squared. If you're confused about that, if you look over at the identity toolbox, you know that sine over cosine is tangent. So sine squared over cosine squared would have to be tangent squared. Plus, cosine squared over cosine squared is 1. 1 over cosine squared would be secant squared. And again, if 1 over cosine is secant, then 1 over cosine squared would be secant squared. This is your 10th tool in your identity toolbox. Tangent squared plus 1 is equal to secant squared. I'm going to do a rewrite on this right here. I'm going to say sine squared plus cosine squared is equal to 1. And I'm going to go through, and instead of dividing by cosine squared as I did before, I'm going to go through and divide by sine squared all the way across. So that would give me 1. And then cosine squared over sine squared would be cotangent squared. And 1 over sine squared would be cosecant squared. Now, just to conform to the way that this relationship is written, I'm going to change up the order a little bit. And instead of writing 1 plus cotangent squared, I'm going to write cotangent squared plus 1 over here. Now, these final 3 tools in the identity toolbox are affectionately referred to as your Pythagorean identities because they're derived from the Pythagorean theorem. But that's it. This is your identity toolbox. It's a listing of 11 expressions that are equivalent. How do you use the identity toolbox? Answer, you substitute. For example, if you have the number 1 in some sort of an expression, you may have cause to substitute sine squared plus cosine squared for that number 1. Now, I want to focus on these last 3 identities, the Pythagorean identities here, and point something out to you that you're going to use over and over and over again. So watch what I'm going to do. And I want you to understand that I'm not really adding to the toolbox here. I'm just taking 3 of the tools that we have and re-expressing them. So if you want to think of them as completely different tools, you can, but I wouldn't. Look, if the sine squared plus the cosine squared is 1, then we know that 1 minus the sine squared is equal to the cosine squared. We also know that 1 minus the cosine squared would be equal to the sine squared. So these are really different ways of writing that exact same relationship or equation. So if you're going to be solving some sort of an identity proof or some sort of a problem where you're simplifying an expression and you're going to be substituting, you could, for example, substitute 1 minus cosine squared for sine squared. Or you could, for example, substitute 1 minus sine squared for cosine squared. I'm going to do a similar rewrite on each of these. You follow along here. If the tangent squared plus 1 is the secant squared, then you could say that the secant squared minus 1 would have to equal the tangent squared. And that the secant squared minus the tangent squared would have to equal 1. Same equation, just written 2 different ways. 2 other ways. And here I could say that the cosecant squared minus 1 would give you the cotangent squared, and or the cosecant squared minus the cotangent squared would give you 1. So once again, at some point in the future, you're going to be solving a problem, and you're going to have in your problem, you're going to have a tangent squared, and you're going to have reason for substituting secant squared minus 1 for that tangent squared, which you would just be able to do. You'd be able to do that. Now, I'm not quite done here. I want to circle this. And I'm going to point something out to you of an algebraic nature. If it wasn't important, if it didn't happen a lot, if you didn't need to apply what I'm about to tell you over and over again, I wouldn't make a big deal out of this. But I need to point this out to you. In these relationships here that I'm gesturing to, you have a whole lot of these. Difference of squares. 1 minus sine squared. 1 minus cosine squared. Secant squared minus 1. Secant squared minus tangent squared. Cosecant squared minus 1 and cosecant squared minus cotangent squared are all difference of squares. And you know that difference of squares factor into conjugates. So what I'm trying to tell you is, let's suppose you have 1 minus sine squared of some angle theta. You know that would be the same thing as 1 plus the sine of theta times 1 minus the sine of theta, because these are the conjugates that would multiply to give you that difference of squares. On the other hand, let's suppose you have secant of x minus tangent of x times secant of x plus tangent of x. When you multiply those, you're going to get the difference of squares. Secant squared of x minus tangent squared of x, which would equal 1 per this tool in your identity toolbox. So I guess just to state it here and be able to move on. These are the 11 tools that you are responsible for knowing. If you're thinking that you have to memorize this by writing them over a few times, then do that. The first 8 you already knew. The bottom 3 are just Pythagorean theorem relationships. And then when you do a rewrite on these 3, you're going to end up with expressions that involve difference of squares. And I can tell you that difference of squares are going to come to play in many, many of your problems. You're going to have to know that they factor into conjugates, and you're going to have to know that when you multiply the conjugates, you get the difference of squares. Okay, so this toolbox that I just created here, I'm going to slide it off camera, but occasionally I'm going to slide it back on so I could point out to you which tools in the toolbox we're going to use. But I'm going to go ahead and do some problems for you. All right. This is going to be the directive. The directive is going to be simplify. So I'm going to give you an expression, and you're going to be charged with simplifying the expression. You're going to be using 2 things, the identity toolbox and your finely honed algebra skills. So, example, I've got the tangent squared of theta plus the sine squared of theta plus the cosine squared of theta. And I'm charged with simplifying this expression. Let me pause for a moment here. Before I do this, I want you to know something about these types of problems. If there ever was a type of problem that you actually learn by doing, as opposed to just watching someone model it for you, this is the type of problem. These types of problems where you're asked to simplify, as well as the next type of problem we're going to do where you're solving identity proofs, you learn by doing. You kind of have to struggle through several problems before you develop a knack for doing them. You learn what works and what doesn't work by actually trying to do the problems. You'll try to do one problem and you'll realize that your method that you've decided upon isn't going to work for you, so you'll have to use that eraser on the end of your pencil, start over, and come up with a different approach. These problems you learn by doing. I've taught these for a long time, many times over, and I can tell you this, these problems are particularly challenging to a group of students who does not like to put in the sweat equity, who doesn't like to put in the time and the practice. You can't just watch me do it and then think that you're going to know how to do it. You actually have to spend time doing these problems. I'm just telling you that because I don't want anybody to fall down here. You're all doing really well in this class. When I teach this unit and then I give the final assessment, I give the quiz on this, on identity proofs, I can tell you that I have students who do extremely well and get A's, maybe don't even miss any points, maybe even get a bonus or 2 and get over 100. But I can tell you also that every year I have students who fail the final assessment. And it's usually the students who haven't put in the time to learn how to do it. So I'm sure you're tired of hearing me talk about it. I just wouldn't feel good if I didn't mention this to you. These problems you learn by doing. As you do these problems, one of the things you'll find is that there's never going to be just one way to do these. I'll demonstrate one way. You might be thinking another way. Your method may be more efficient than mine. What we're looking for is a method that doesn't violate any algebra rules, and we're looking for a method that uses the tools in the identity toolbox. So I'm charged with simplifying this expression. And here's what I notice. I notice this part of the expression right here. This sine squared plus cosine squared is this identity right here. So what I'm going to do is I'm going to substitute 1 for that. So when I substitute 1 for that, I'm going to have tangent squared of theta plus 1. This is another identity. Tangent squared plus 1 is equal to secant squared. So what I would do to finish this problem out is I would substitute secant squared for tangent squared plus 1. That is the final simplified expression that started as tangent squared plus sine squared plus cosine squared. Please understand, if you would enter this in your calculator, and you would enter this in your calculator, and maybe you graph this as y sub 1 and you graph this as y sub 2, those two graphs are going to be the same. Tangent squared plus sine squared plus cosine squared is the same as secant squared. That's what that means. Onward we go. Another example. 1 minus the sine squared of x minus the cosine squared of x. Here's what I see when I look at this. I see this part of the expression. And I know that 1 minus the sine squared is equal to the cosine squared. So I'm going to substitute cosine squared for 1 minus sine squared. So I'm going to put cosine squared right here instead of the 1 minus sine squared. And then cosine squared minus cosine squared would simply be 0. Next one. The sine of A plus the cosine of A, quantity squared, plus the sine of A minus the cosine of A, quantity squared. Here's what I'm thinking. I'm thinking that I should go ahead and square this binomial and square this binomial and see what happens. The algebra skill here is squaring a binomial. You guys know the pattern. First term squared would be sine squared. First term times second term doubled would be 2 sine of A, cosine of A, and then second term squared would be cosine squared of A. I'm going to follow the same pattern here. I'd have plus sine squared of A minus 2 sine of A, cosine of A, plus cosine squared of A. Once again, all I did was square the first binomial and square the second binomial. Now, here's what I notice. This guy right here is the opposite of this guy right here. They would cancel out, so to speak, and give me 0. They're gone. Then this sine squared here, combined with this cosine squared, is this identity. Sine squared plus cosine squared is equal to 1. So I'm going to substitute 1 for those two guys. And I got the same thing here. One plus 1 is 2, and I'm home. Next example. Let's see. The secant of beta plus 1 times the secant of beta minus 1. Now, I immediately recognize these two as conjugates. If I FOIL them or multiply them, I'm going to get the difference of squares, secant squared of beta minus 1. This expression is an identity. Secant squared minus 1 is tangent squared. So secant squared of beta minus 1 would have to be tangent squared of beta, and I'm home. Next example. Let's see. 10 times the secant squared of alpha minus 10 times the tangent squared of alpha. One of our essential algebra skills is the ability to identify common factors. So when you look at this, what you need to see is that common factor of 10. So the first thing I'm going to do is factor out that 10. And in the quantity, I'm going to have secant squared of alpha minus tangent squared of alpha. That's an identity. It's one of my tools. Secant squared minus tangent squared is 1. So this just becomes 10 times 1, which is 10, and I'm home. Next example. Let's see, I've got tangent squared of x times the cosine of x plus the cosine of x. Like in the last problem where we had a common factor of 10, what you need to see in this problem, we have a common factor of cosine. So I'm going to factor out the cosine. So I have the cosine of x, and then inside the quantity, I'm going to have tangent squared of x plus 1. Tangent squared plus 1 is secant squared. That's one of my identities. So I'm going to say this becomes the cosine of x times tangent squared plus 1 is secant squared of x. Cosine is the reciprocal of the secant. So I'm going to take and substitute for cosine. Cosine, this is what I'm going to use. The cosine is 1 over secant. So I'm going to substitute 1 over secant for that cosine. So I'm going to have 1 over the secant of x times the secant squared of x. Now this secant in the denominator cancels one of these secants upstairs. So my final is going to be secant of x. Next example. Let's see. Secant of theta times the quantity 1 plus the sine of theta times the quantity 1 minus the sine of theta. Okay, here we go. These two guys are conjugates. I'm going to go ahead and multiply them and get the difference of squares. So I'm going to have the secant of theta, and then 1 plus sine times 1 minus sine would be 1 minus the sine squared of theta. But 1 minus sine squared is cosine squared. So I'll substitute cosine squared for this quantity here. So I'm going to have the secant of theta times cosine squared of theta. Now, just like I did in the last problem, I'm going to substitute 1 over secant for cosine. Here I'm going to substitute 1 over cosine for that secant. Now, this cosine in the denominator would cancel one of these cosines in the numerator, and I'm home. The final would be the cosine of theta. All right. Look at this one. I've got the sine of x over the tangent of x. You know, one thing I could do here is I could use this identity, that the tangent is equal to sine over cosine. So I'm going to substitute sine over cosine for tangent. Now, when I do that, I'm going to form a complex fraction, but that's okay. I know how to handle that. So what I'll do here is I'll say this is equal to the sine of x over, and then for this tangent in the denominator, I'm going to substitute the sine of x over the cosine of x. When you have a situation where you're dividing by a fraction, the vast majority of the time, you're going to switch that over to multiplying by the reciprocal. So I have the sine of x, I'm going to change to multiplying, and I'll flip this guy over, the cosine of x over the sine of x. Then this sign in the numerator cancels this sign in the denominator, and I'm done. Final answer would be the cosine of x. Let's do another one here. It's probably very similar. Let's suppose we have the cosine of beta over the cotangent of beta. Cotangent is cosine over sine. I'm going to substitute cosine over sine for that cotangent in the denominator. So I'm going to have the cosine of beta over. Then I'm substituting cosine of beta over sine of beta. I'm going to switch to multiplying by the reciprocal. So I'd have the cosine of beta. This cosine of beta is this cosine of beta right here. Times, and I'm flipping this over, the sine of beta over the cosine of beta. These guys cancel, and I'm left with just the sine of beta. Now, some of these problems seem to be pretty straightforward, not very challenging maybe. You look at them and it's fairly evident what it is that you're supposed to do. The identity that you're going to use jumps right out at you. That's not always the case. I don't want you to think it's all the case. It's always the case. Some of these problems can be a little more challenging. Let's look at this one. I've got the tangent of x times the cosecant of x all over the secant of x. So here's what I'm going to do. I know that the tangent is sine over cosine. So I'm going to substitute sine over cosine for that tangent right there. I know that the cosecant is 1 over sine. So I'm going to substitute 1 over sine for cosecant. And I know that the secant is 1 over the cosine. So I'll substitute 1 over cosine for that. So I'm going to do 3 quick substitutions here. On the top, the tangent becomes sine over cosine. The cosecant becomes 1 over sine. And in the denominator, the secant becomes 1 over cosine. Now look, this sine cancels this sine. So you're going to end up with, upstairs, you're going to have 1 over cosine. And in the denominator, you have 1 over cosine. And of course, that would equal just 1. All right, let's do a couple more. Tell you what, we'll do 2 more. And each of these, I think, is maybe just a little more involved than some of the ones we've already done. But I wanted to give you just a little taste of some problems that maybe aren't as straightforward. Some that have a little twist to them, involve a little more. So here we go. All right, now watch carefully. Step number 1, I'm going to substitute for tangent, sine over cosine, and I'm going to substitute for cotangent, cosine over sine. So when I do that, I'm going to have 1 plus the sine of x over the cosine of x. And then downstairs, I'm going to have 1 plus the cosine of x over the sine of x. All right, now, upstairs I have the number 1 plus a fraction. Downstairs I have the number 1 plus a fraction. Here's what I'm going to do. I'm going to go ahead and combine those. And of course, you know that when you combine those, you have to get a common denominator. So this one right here, I'm going to express as cosine of x over cosine of x plus sine of x over cosine of x. And this one right here, I'm going to express as sine of x over sine of x to get a common denominator. So that what that gives me upstairs is cosine plus sine over cosine. And what that gives me downstairs is sine plus cosine over sine. Now I'm at the point where what I'm going to do is I'm going to multiply by the reciprocal. So I'm going to have the cosine of x plus the sine of x over the cosine times, and I'm going to take the reciprocal of the denominator, and that would give me a sine of x over sine of x plus cosine of x. What you need to note here is that this numerator is the same as this denominator. So those common factors cancel, which leaves me a sine of x upstairs and a cosine of x downstairs. But sine over cosine is tangent, and I'm home. So that one was a little bit more involved. Let me do one more for you. I've got the secant of x plus the tangent of x. And downstairs, I've got the secant of x plus the tangent of x minus the cosine of x. All right. So here's what I'm going to do. I'm going to start by substituting. For secant, I'm going to substitute 1 over cosine. For tangent, I'm going to substitute sine over cosine. I'm going to substitute 1 over cosine for that secant, sine over cosine for that tangent right there. That should be tangent. All right, so here we go. All I'm doing is substituting from my identity toolbox. Secant would be 1 over the cosine of x, plus tangent would be sine of x over the cosine of x. And that's all going to be over this secant, which is 1 over the cosine of x, plus this tangent, which is sine of x over the cosine of x, minus the cosine of x. And you know what I'm going to do? I'm just going to put that over 1 so it looks like we have another fraction there. Now, upstairs, I have the same denominator, so I can write that as a single fraction. So upstairs, I'm going to have 1 plus the sine of x over the cosine of x, fraction bar. Downstairs, I've got cosine of x for a denominator, cosine of x for a denominator, and the denominator here is 1. So here's what I'm going to do. I'm going to take this cosine of x and I'm going to multiply by a strategic form of 1, cosine of x over cosine of x, in order to get a common denominator. So that would give me, on the bottom, this 1 plus this sine of x minus cosine times cosine would be cosine squared of x, but each one of those fractions now has the same denominator. So I'm going to write it as one fraction and put them all over the cosine of x. Time to multiply by the reciprocal. So your top fraction here is 1 plus the sine of x over the cosine of x times. I'm flipping this guy over, so I'm going to have the cosine of x over 1 plus the sine of x minus the cosine squared of x. This guy cancels this guy. So that leaves me with 1 plus the sine of x over 1 plus the sine of x minus the cosine squared of x. Now, here's what you might not see right away. If you take this 1 right here and you group it with this minus cosine squared, 1 minus cosine squared is an identity. 1 minus cosine squared is sine squared. So I'm going to substitute sine squared for the 1 minus cosine squared. So when I do that, I'm going to have still on top 1 plus the sine of x. But in the bottom, this 1 minus cosine squared becomes sine squared plus this sine of x. What you need to see now is that between these two terms, there's a common factor. And we are always on the lookout for one of those. So I'm going to factor out that sine of x. So I have 1 plus the sine of x over. When I factor out the sine of x, I'm going to have the sine of x. And then in the quantity, I'm going to have the sine of x plus 1. And what you need to see now is that this cancels this. Those are the same. So that leaves you with a 1 on top and just this sine of x on the bottom. But 1 over sine is cosecant. And now we're home. So certainly this last example problem was far more involved than the very first problems we did. Let's run through some of these real quick, and we'll call it a day. Here, we substituted 1 for sine squared plus cosine squared. Students, as soon as you start seeing sine squareds and cosine squareds, that's the cue or the clue that you're going to use this Pythagorean identity here. Sine squared plus cosine squared is 1. Once again, if sine squared plus cosine squared is 1, then 1 minus sine squared would be cosine squared. Here we're using an algebra skill squaring a binomial. Here we're using an algebra skill multiplying conjugates. Here we're using an algebra skill looking for a common factor. In this case, it was 10. Same story on this one. The common factor was cosine, so we factored it out. Here we multiplied conjugates. Here we substituted 1 over cosine for secant. Here we substituted sine over cosine for tangent. Similar type substitutions through these last couple example problems here. Here we're multiplying by the reciprocal, another algebra skill. Getting a common denominator right here by multiplying by strategic forms of 1, another algebra skill that comes to play. And then this very last one, there's probably 3 or 4 algebra things going on, and a couple different times we had to go to the identity toolbox to do substitutions. So these are the types of problems that you're going to be expected to do. These problems where you're asked to simplify, are sort of precursors to the identity proof problems. I'm going to post for you a practice, and I'm hopeful that this video is going to help you solve those problems on the practice sheet. So gang, thanks for your attention. Good luck on the practice sheet. Remember what I said, you don't put the time in on these, you're going to suffer a little bit. The only way you're going to learn these is by doing them. And everybody kind of struggles through, but if you do them, it's going to pay off for you. All right, thank you for your attention. Bye.